Okay, so more accurately than saying z is 2.9, we see that the z values corresponding to 0.498 go from 2.81 to 2.96. Look on your z table, you'll see if you see z equals 2.81, you're going to see area 0.498. For z equals 2.96, you look, you're going to see area 0.498. This means that we're not sure which of these values, although we kind of think a z value somewhere in the middle of these is going to be the one that best corresponds to area 0.498. We're just going to look at a range. We're going to say, okay, if it was 2.81, what would the height be? If it was 2.96, what would the height be? Well, the delta z, that's from z equals 2, then is going to be between 0.81 and 0.96. Over here we see why it was 0.9, because if you go from 2 to 2.9, that's how far you go, 0.9. Now, if we're looking at both 2.81 and 2.96, well, 2.81, you got to go 0.81 from 2. 2.96 is 0.96 from 2, so that this z here would be maybe 2.81, maybe it would be 2.96. Okay? Well, it follows then that our change in x from x equals 84, which corresponds to the z equals 2, has to be between 0.81 times 3, which is 2.43, and 0.96 times 3, which is 2.88, if I've done my arithmetic correctly, so check me on that. So, when z was 2.9, our change in x was 2.7 inches. Okay? Now, z is a little less than that, 0.81, the change is only 2.43 inches. And if z is 2.96, then we're going to get a little more than this. We're going to get 2.88 inches, but the calculation is done using the same intuitive reasoning that we used here. So we have now a picture where z equals 2 here and z equals 3 here. And we've marked off z equals 2.81 and z equals 2.96. I didn't write the z equals on these, but let's go ahead and put that in. I wasn't sure how much room I'd need because I hadn't predicted all my labeling, but I decided then to label these arrows up above the axis. So instead of just a picture with 2 and 3 here and 2.9 here, we have a picture with 2 and 3 here, 2.81 here, 2.96 here. Now, how far is it from here to here? Well, from here to here, the change in the value of z is 0.81. To go from 2 to 2.81, we have to change z by 0.81. If we change z by 0.81, then x is going to change by how much? Well, it's going to change by 0.81 times 3 inches, or 2.43 inches. It's easy to calculate, and it should make some sort of sense to you. And if it does, then this is easier than it will be if you've got to rely on memorizing a formula. Okay, and then from z equals 2 to z equals 2.96, what's delta z? Think about it, don't read it. Yeah, okay, well, it's 0.96. To go from here to here, we've got to move 0.96 z values, which is 0.96 standard deviations. And we can do that up here. Your delta x is then 0.96 times 3 inches, or 2.88 inches. Then, since this is at x equals 84 inches, well, 84 inches plus the 2.43 inches puts us here at x equals 86.43 inches. So we can conclude that x equals 86.43 here. And here, x equals 86.88 here. And now we've got a range of x values from 86.43 to 86.88, and we expect that our tallest player out of 5 might well be within that range, although we don't have a huge amount of confidence because all kinds of things happen. People's height changes if you measure them at different times of the day. So our best guess, though, is that if these 500 players really have normally distributed heights, that we're going to have someone that's around 86 and a half, maybe even approaching 87 inches. Now that would be what, 7 foot 2 and a half, 7 feet 3, because 84 inches is 7 feet. There are players in the NBA taller than that. Those aren't atypical values, but that puts you into the range of some of the tallest players. Okay. And here, we also figure this based on the middle, which is much closer to the way the formula works. So we'll talk about that in the next clip.